Okay, 2000.
So now the university is generally closed there, right?
Yeah, here also.
Here it's not closed. Here,
Oh,
like I go every day, so that's why I
okay.
asked you to shift my time.
Maybe they control the spreading level, eh?
No, no, it's seeing second wave now
Oh, okay,
in Japan.
okay. Here now the top level.
Yes, I am reading about that
Yeah,
daily.
yeah. Every day is increased, not controlled. Maybe it will take 2 more months at least.
Let's just hope it gets
Yes,
good
yes,
fast.
exactly, exactly.
Yes, yes.
Shall we start? Kamlan, Dr. Kamlan.
Sir, you can start, sir.
Okay. Um, okay, Namrata, I am going to give normal formal introduction.
Okay.
Yeah. Good evening, everyone. Once again, once. Okay. Once again, welcome to all this 2 days international virtual seminar on recent advanced material and energy applications, organizing by Center for Nanoscience and Technology, Sadiva Ministry of Science and Technology. Dr. Namrata Pand will be deliver her talk as a first speaker of this session. Dr. Namrata Pand currently working as a postdoctoral researcher at the Institute of Chemical Research, Kyoto University, Japan, in the field of lead-free perovskite solar cells. Dr. Namrata Pond has completed her PhD from National Institute of Material Science, that means now called NIMS. It is a very familiar institute in the material science in Japan, in March 2020. Her PhD research work was mainly focused on inverted structure perovskite solar cells and a nickel oxide based whole transport layer. She also worked with the Professor Jun Takaya. He is one of the well-known professor in the perovskite solar cell in Japan and University of Tokyo, Japan, in the research area of polymer and perovskite thin film based transistor under the scheme of visiting researcher. Dr. Namrata Pand has published several papers in a reputed international journal and conferences. Before going to her talk, once again I request to all the participants that if you have any questions during the lecture, kindly post in the chat box. The speaker will respond to your question at the end of the session. Also, we will share the feedback form at the end of the session. Please fill it before leaving the session. Dr. Namrata,
Yes.
okay, you can start now.
Oh, thank you, Dr. Murugadas, for such a nice introduction. So let me begin. And the topic for today's talk is nickel oxide hole transporting layer for lead-based perovskite solar cells. And here is the outline for today's presentation. I have broadly divided it into three sections for the clarity and convenience of understanding. So in the first section, I give a general introduction to perovskite solar cells and progress in the perovskite solar cell research, and talk about the types of device architectures and emphasize on organic and inorganic hole transporting materials. In the next subsequent sections, I talk in detail about the significance of using nickel oxide as a whole transporting material. And finally, I talk about the challenges and the results of my experiments for overcoming the limitations of sputtered nickel oxide based perovskite solar cells. So as most of you might be knowing that perovskite is a generic term for any compound with a general formula of calcium titanate, CaTiO3. The mineral was first discovered in the Ural Mountains of Russia by Gustav Rose, and in 1839, he discovered it in 1839, and it is named after the Russian mineralogist Lev Perovsky. And all the materials with the same crystal structure as CaTiO3, which is shown in the figure below. So this structure is generalized as ABX3, and any material, any compound that has this structure is termed as perovskite. So coming to perovskite solar cells, the working mechanism for these is the same as for any other photovoltaic technology. So it is based on the photovoltaic effect, where when the sunlight falls on the absorber layer, electrons and holes are generated, and a voltage across the PN junction is formed. So coming to discuss about the specific working in the perovskite solar cells. Here, the perovskite is the solar absorber layer, and it is sandwiched between a p-type and an n-type semiconductor. So when the light falls on the perovskite absorber layer, the electrons and holes are generated, which is unlike in the like we see in the silicon cell where only one type of carriers are generated. Perovskite has the advantage that it can create both the electrons and holes, and from there they are further transported to the charge transporting layers, which further transported to the electrodes to complete the circuit. So the progress in the perovskite solar cell power conversion efficiencies has been quite remarkable. And as we can see from the figure at the topmost corner in the left side, this is the famous chart from National Renewable Energy Lab, and it shows that the perovskite solar cells has seen an accelerating growth. So it has reached an efficiency of 25.2% in less than a decade. And this is remarkable, I emphasize again, because we are now at the same standard as the silicon solar cells. So silicon solar cells have been existing in the market since last 50 or more than 50 years. And to reach up to that level in less than 10 years is quite an achievement. And it is due to the exceptional optoelectronic properties of the perovskite, like the high optical absorption coefficient, long carrier diffusion length, high charge carrier mobility, tunable band gap, and the ease of deposition by simple solution process. So this is what make these properties is what makes the perovskite such a wonderful material. And additionally, it has the advantage that it can be incorporated into different device architectures, which we'll see in the further slide. So if we have to categorize the perovskite solar cells into different device configurations, we can majorly classify them into planar and mesoporous scaffold structure, and both can be further classified into inverted and regular device structures. So to clarify the terminology used in detail, let me, okay. So if we see the figure A and B, these are the planar structure. So what I mean by planar structure is that the perovskite is deposited on top of a substrate or on top of an underlayer, which is plain or smooth. And a mesoporous scaffold structure, as we can see in figure C and D, it is deposited on top of a mesoporous type of an underlayer. So now coming to the inverted and regular structure, it depends on the type of the semiconductor, like p-type or n-type. Depending on which semiconductor it is deposited, it governs whether it is a regular and inverted structure. Or to further elaborate it more, when the light penetrates the perovskite by first entering the p-type semiconductor, it is called a PIN configuration or a inverted configuration. Whereas a regular configuration is the one in which the light first passes through n-type semiconductor before penetrating the perovskite, and that is called an NIP structure. So NIP is the regular structure, whereas PIN is the inverted structure. Why we need to study the structures in detail is because to understand the factors governing the device performance, these device architectures are very important. So as we can see in the figure, the charge carrier dynamics, charge transport, energy alignment, hysteresis, device stability, and morphology control of the perovskite are all dependent on the device architectures. And in order to enhance the performance, it is important to study the device architecture and the interfaces associated in each device architecture. So now, since since we now know the device architecture, and we now know that for inverted and regular structure, we need to study the type of underlayer. Here I emphasize on the whole transporting layer. As in the next slides, I'll talk about the inverted structure where the whole transporting layer forms my underlayer. So the underlayer or the HTL in the inverted device architecture facilitates charge transport from the perovskite absorber layer to the counter electrode. It blocks the transport of electrons, protects perovskite layer from moisture and oxygen, influences the VOC by determining the quasi-Fermi energy level. So to have an ideal HTL, it should have compatible energy levels like the HOMO and LUMO with the neighboring charge transporting layers. It should have optical transparency in visible spectrum, which is quite necessary for inverted structure. Should have a decent hole mobility to conduct the hole and prevent charge recombination, and should have a high thermal and morphological stability. And of course, like everything, we need to reduce the cost. So it should be easy. It should be less expensive, so that we can have an easy scaling up of the technology. So the HTLs that are used for the inverted device architecture are mostly the PDOT-PSS, PTAA, or nickel oxide. And like we know, they are either they can be organic or inorganic. So comparing the organic whole transporting layer with the nickel oxide, we can see that the PDOT, which is an organic HTL, is acidic in nature, has low device open circuit voltage, and it hampers the perovskite long-term stability. It is not suitable for roll-to-roll production, and it is quite expensive. On the other hand, nickel oxide is highly transparent. It has a wider band gap. Due to its inorganic nature, it is highly stable, comparatively low cost, gives a high device open circuit voltage, and it enhances the long-term stability. Here are a few more properties of the nickel oxide, and like why it is a suitable transparent conductive oxide. So at first, the pure stoichiometric nickel oxide is actually a Mott-Hubbard insulator. So it should not be technically used as a p-type semiconductor to transfer the charges to the electrode. But the presence of excess oxygen due to the presence of species like nickel oxide, hydroxide, and Ni2O3 makes it a non-stoichiometric material, and it is denoted as nickel NiOx. The work function for the nickel oxide is 5.4 electron volt, and it has a wide band gap ranging from 3.6 to 4 electron volt, enabling it to be highly transparent in the near ultraviolet and visible range. The transmittance of nickel oxide is quite high, which is more than 80% in the entire wavelength range, and it is easy to fabricate, and it is quite cheap. The fabrication technique required is not as expensive as for the silicon. So now, emphasizing particularly on the nickel oxide, first we need to see this, we look at this efficiency chart for the perovskite solar cell power conversion efficiencies. And till now, the highest efficiency that has been recorded is based on an organic whole transporting layer in the regular structure, that is the spirometate. So we can see that we have 25% power conversion efficiency. Comparing it to the nickel oxide, the nickel oxide based cells have relatively lower power conversion efficiency. So the blue and the pink dots show the nickel oxide based perovskite solar cells, where the blue dots correspond to the solution process nickel oxide. And if we compare the pink and the blue dots, we see that for the sputtered nickel oxide, the efficiency is further low. It is 15%, whereas the highest is 25%. So this chart is for the perovskite solar cells with only lead perovskite. And of course, changing the composition can change the efficiencies. So it is important to, so now the question is that we need to address and we need to find out why the efficiencies are low for the sputtered nickel oxide case. In order to further enhance or contribute to increasing the sputtered nickel oxide based perovskite solar cells. So to understand that, we carried out a series of investigations, and to begin with, we sputtered a nickel oxide with optimized condition. So we obtained a nickel oxide with a highly transparent, highly transparent nickel oxide with a transmittance of nearly about 80% in the visible region. And from the XRD and the SEM image, we could confirm that we have obtained a uniform nickel oxide structure. The next step was to deposit the perovskite film, and for that we adopted the one-step deposition method. In this method, the perovskite solution is dropped on the nickel oxide substrate, and it is spin coated and annealed on a hot plate at a temperature below 100 degrees centigrade. And during the annealing step, the excess of solvent of the solution evaporates, and we have and the crystallization of perovskite begins on top of the nickel oxide surface. Here is a schematic showing the steps we incorporated for the perovskite film deposition. So we had three conditions. We chose three conditions for the perovskite film preparation. We used a stoichiometric ratio of precursors as in figure A. We used 1:1 PbI2 NMAI. Second, we changed the stoichiometry. We increased the amount of the methyl ammonium halide, and in figure C, we again used the stoichiometric ratio, but compared to the A and B figure, where we see that the annealing is directly in its own atmosphere at 100 degrees Celsius. In figure C, we have used a vapor atmosphere of methyl ammonium chloride and methyl ammonium iodide. And here is the result for all these conditions, where we see that when we talking about the figure A and the corresponding, we can see that when we are changing the amount of methyl ammonium chloride, we can see a clear shift or clear difference in the peak intensities of the characteristic peaks. And similarly, if we compare all the other conditions, we can see the variations. So from these figures, and the XRD image, we see that the best film was obtained when the MAI is to PbI2 ratio was 1:1, and annealing was done under a methyl ammonium chloride vapor atmosphere. So from here, we concluded that looking only at the XRD and the SEM, we concluded that the perovskite films obtained with the equimolar ratio of precursor materials showed additional white grains and prominent remnant PbI2. And with MaCl or MAI additives in the non-stoichiometric precursor ratio, we could see an improved crystallinity and enhancement in the grain size was observed. And similar results were observed when the perovskite films were annealed under Ma plus halide vapor atmosphere. So from here, we see that the methyl ammonium chloride vapor atmosphere is acting as a catalyst for enhanced perovskite crystallinity. Next, we fabricated the entire device and compared the device performance, particularly the JV curves, with each corresponding condition, and observed that while we vary the MaCl concentration in the perovskite solution, we get the highest or the best performance when we have 0.3 molar excess MaCl. And when we vary the MAI concentration, we find that 1:1 stoichiometric ratio is the best, and we don't need excess of MAI in our precursor solution. But comparing it to the vapor annealing condition, we see that the performance increases manifold, and we get the best JV curve for the perovskite solar cells, which has been annealed under a methyl ammonium chloride vapor atmosphere, and it has a stoichiometric ratio of 1:1 for the PbI2 and MAI. So in summary for this, we see that addition of excess Ma component in the precursor shows poor JV characteristic curve. And when we have the precursors in 1:1 ratio, we have the best device performances. So we, as from the previous slide, we can see that the best out of all the JV curves, we have the best performance for the one with the methyl ammonium chloride vapor treatment. We further characterized the device only comparing the perovskite that is annealed under the methyl ammonium chloride vapor atmosphere and which is annealed in its own ambient atmosphere. So here, when we look at the device cross section, we see that in the figure B, we can, this is the perovskite, this is the cross-section image of the perovskite which was annealed under the methyl ammonium chloride vapor treatment. We can see that we have quite uniform grains and smooth interface without any defects. Whereas when we observe figure A, it has the perovskite that was annealed without any atmosphere. We see that the grain boundaries are not well defined, and additionally we can see that there are some defects at the interface, especially there is a void in the upper interface that is between the perovskite and the ETL, or the ETL in this case is the PCBM. So this explains why we have a lower performance when we are using the perovskite which is annealed as such, and why there is an enhancement in the efficiency. So of course, when the interfaces are smooth, the transport of electrons and holes towards respective electrodes is more smooth. And that is what we want in our device. The better transport, the better efficiency. So when we made a batch of around 30 devices, and we observed that for all these devices, whenever we have an methyl ammonium halide vapor atmosphere, the devices perform better. And we compared the VOC by varying the light intensity and calculated the ideality factor. And we saw that for the methyl ammonium chloride vapor atmosphere, we have an ideality factor near to 1. So okay. So ideality factor determines the number of radiative recombinations or number of defects. The closer the value is to 1, we have lesser number of defects, or we have a lesser number of non-radiative recombinations. So since the ideality factor for the with MCVT or methyl ammonium chloride vapor treatment is nearer to 1, we can confidently say that we have reduced number of defects. And further, when we looked at the JSC versus the light intensity ideality factor, again, we have a value nearer to 1 for the perovskite annealed under the methyl ammonium chloride vapor treatment. So this clearly shows that the vapor atmosphere treatment reduced the number of defects, and all the device parameters were enhanced. Like we can see from the table below that we had a good improvement in the JSC. Of course, open circuit voltage is very important, where we can see we have 10 millivolt improvement, and fill factor is drastically improved, which leads to a power conversion efficiency of 15%, whereas without the annealing treatment, we just had 9.7%. So from the above study, we concluded that the stoichiometric ratio of precursors is important to obtain planar inverse structure perovskite solar cells for the perovskite films deposited by one-step method. And if you want to read more about it, this has been published in Advanced Material Interfaces, and maybe you can look into the details about this study. So from the first study, it was clear to us that the perovskite film has a major effect from the underlayer. And to explore it more, what we did is we adopted another technique, another deposition method to make the perovskite film. So in the first study, where we were using the one-step deposition method, where we just have a one solution, in the next step, we used a two-step deposition method. So here, in this case, a layer of PbI2 is first spin coated on the whole transporting layer, the nickel oxide, and then a methyl ammonium iodide is added on top of this PbI2. So from the schematic, we can see that first the PbI2 is already formed, a PbI2 layer is already formed, and then when MAI is deposited, the MAI penetrates into the PbI2, and then we have a bottom layer of PbI2, and on top of that, we have a perovskite, which is formed by the interaction of the PbI2 and methylammonium iodide. So we compared the deposition techniques and the results from these deposition techniques. So briefly, let me explain the difference once again. In the schematic for the perovskite layer deposition, the first is the one-step deposition method, where we can see we have a one solution and the perovskite is formed immediately after annealing the spin-coated perovskite solution. Whereas in the two-step deposition, we first deposit PbI2, we spin coat it, and then we add MAI, anneal it, and then we have a perovskite. So we have a PbI2 layer at the bottom and a perovskite layer on top. When we looked at the SEM images, we saw a clear and stark difference in the top view as well as the cross section of the perovskite films. So in figure A, we can see that the perovskite grains, in addition to the perovskite grains, there are some white grains, which we assign to the residual PbI2 grains. Whereas for two-step, the morphology is quite uniform and we only see the perovskite grains. And when we look at the cross section of the complete devices, we see that as in the previous study, we saw the voids due to the residual PbI2. We don't see any such voids we see a smooth interface. But we see some white spots like the one in figure A. We see white spots at the bottom interface, that is in between the nickel oxide and the perovskite layer. So when we perform the XRD for these white spots, we find the characteristic PbI2 peaks, and hence we assign the white grains to the residual PbI2. So the difference is quite clear that in the one-step deposition method, we have the residual PbI2 on top of the perovskite, whereas for the two-step, we have the residual PbI2 at the bottom, I think, which is very clear why, because we have a PbI2 layer at the bottom in the beginning. So when we check the optical properties, again, we see the difference that when we measured the steady state photoluminescence, we observe that for the one-step method, the PL peak intensity is quite low, whereas for the two-step method, it is much enhanced. Going to the basic principle of the photoluminescence, the higher the peak intensity, the more number of radiative recombinations. So we need more number of radiative recombinations in the perovskite for the cell to perform well. We want to eliminate non-radiative recombinations, and as non-radiative recombinations act as defect sites, whereas radiative recombinations enhance the performance. So clearly, like we can see from the SEM also, that the crystallinity for the two-step method increased. That means that defects reduced, and this complements the PL result. With reduced number of defects, we have a higher PL intensity. When we normalize the spectra, we can see that there is a blue shift in the, there is a slight blue shift in the PL peak for the two-step method, and a blue shift again corresponds to reduced number of defect sites. And when we further took the time resolved photoluminescence, we observe that the lifetime for the, so here is the lifetime table. The lifetime for the two-step method deposited perovskite is too high compared to the perovskite deposited by one step. So an increased lifetime suggests that recombinations reduced in the bulk of the perovskite. So in total, we can say that with the two-step deposited perovskite method, we have a better perovskite crystallinity. And from looking at these results, we proposed a mechanism that when we have a two-step deposited perovskite, we do not have a direct contact of the perovskite with the underlayer, that is the sputtered nickel oxide. That means as soon as we put another layer on top of the nickel oxide, and we start and the perovskite starts crystallizing on top of that layer, the crystallinity is better. This implies that the surface of the sputtered nickel oxide has some defects, and if we directly crystallize the perovskite on top of that, these defects lead to defects in the bulk, and these defects reduce the performance or lower the performance of the perovskite solar cells. And these defects are the reason why we are observing the PBI2 at the top of the perovskite, which is further causing void in between the ETL and perovskite, thus leading to reduced performance. So when we further characterized the device for the JV parameters, we can see that the JV curve for the two-step is clearly much sharper, and we have a closer value of the ideality factor for the two-step deposited perovskite. And looking at the IPCE and the IQE spectra, we can see that we have a higher IPCE coverage, and IQE also increases. So next, the active area for these devices was quite small, 0.185 centimeters square. So the next target was to make a bigger cell with active area of 1 centimeter square. And here in this figure, we have a device with active area of 1 centimeter square. And very surprisingly, we could achieve almost the same efficiency with the two-step method and using the 1 centimeter square active area. So even though previously with the methyl ammonium chloride vapor treatment and one-step method, we could obtain 15%, but without methyl ammonium chloride vapor treatment, we were still at 9%. So here we have not used any vapor treatment, and we simply compared two-step and one-step method and obtained a higher efficiency for two-step method. So that means there are some defects which are treated by either the methyl ammonium halide vapor treatment or by passivating the surface of nickel oxide. So from the two studies, the cumulative conclusion we got is that the location of residual PBI2 governs the device performance for the inverted structure perovskite solar cells with sputtered nickel oxide hole transporting layer. So the next thing is to look at the surface of nickel oxide even more clearly. Since we have already up to now, we have figured out that the bulk defects in the perovskites are arising from the surface. We tried to change the conditions at the surface of nickel oxide before depositing the perovskite. So here we have first we have taken three different surface treatments and compared it with the as sputtered nickel oxide substrate. The first, the three conditions are using the plasma, oxygen plasma on sputtered nickel oxide, using the UV ozone, and using the isopropanol as a liquid for treating the surface of sputtered nickel oxide. And we saw that, and the major, why we chose these three treatments as compared to many other treatments reported by different papers is that these are easier to do, and these are faster, and these do not involve any chemicals like potassium chloride or NaCl. So, and from different literature, it has been reported that these treatments can influence the surface charges of the metal oxide layers. So when we treated the nickel oxide with these conditions, we saw, and we prepared a perovskite layer, we saw that there is no such change in the perovskite crystallinity or the morphology. As we can see from the XRD, we have the peaks are almost similar, no additional peaks and no change in the peak intensities. Even if we look at the SEM images, we observe that we have almost similar size of grains, and all the perovs and they are all uniform. So when we look at the device performance, and here is the box plot, we see that comparing the plasma treated nickel oxide with others, plasma treated has a much better performance. The JSC is significantly higher. VOC is much higher, and the fill factor, and of course the device performance. Just next to it is the UV ozone treatment. So definitely, even though we do not observe any change in the perovskite properties, but we see a difference in the uh, device performance. So it was important to understand the surface chemistry of nickel oxide after the treatment. So for that, we measured the X-ray photoelectron spectroscopy. And from here, it was quite clear what might be happening. So like in the previous results, we were getting a hint that the surface of nickel oxide is influencing. Here we see that with different uh, treatments, we have a different ratio of nickel 3 plus is to nickel 2 plus ratio. We have a different ratio of these species on the surface of nickel oxide. And these species are governing what is happening during the interaction of the perovskite and the nickel oxide. So when we have the as sputtered nickel oxide, the Ni3 plus is to Ni2 plus ratio is the lowest, and with plasma we have the highest. And this explains why we have the highest performance for the plasma treated nickel oxide. So it is important for me to mention here, even though these are not fixed ratios, we need to optimize it. We do not want too high of either of these. We need a balanced ratio, and definitely to achieve this ratio, we need to optimize the sputtering power or the plasma condition inside the sputtering machine or the oxygen flow rate. So if we have an optimum level of Ni3 plus is to Ni2 plus ratio, we can get a good device performance. From here, we concluded that the surface treatment is an effective way to control the surface properties of sputtered nickel oxide, and the incorporation of surface treated nickel oxide can further enhance the device performance of the perovskite solar cells. So in total, from these series of investigations and the experiments that we did, we concluded that during the one-step deposition of lead iodide perovskite, equimolar ratio of precursors should be used to obtain the best performing devices. Additionally, to compensate the loss of Ma+, that is methyl ammonium species, while annealing the perovskite film, which also led to the formation of unreacted PbI2, the film should be annealed in the presence of Ma+ vapor atmosphere. And the difference in perovskite film properties are observed when employing different deposition methods. It was concluded that the surface of nickel oxide plays a major role in defining the nucleation of perovskite on its surface. And the surface treatment of sputtered nickel oxide is an effective way to enhance the performance of the solar cell device. And of course, the presence of nickel 3 plus species promotes hole transfer through the nickel oxide and makes it more suitable p-type conductor, as we could see that the Ni3 plus is to Ni2 plus ratio was the highest for the plasma case. So of course, the ratio is never fixed, but we definitely need a higher Ni3 plus as compared to Ni2 plus. So this makes it more suitable p-type conductor, and the best performance was obtained for plasma treated. Yeah, as I said that we have the highest ratio for Ni3 plus species. So this was the result of the investigation I did for the nickel oxide hole transporting layer for my lead-based devices. Okay, thank you for your attention. And if you have any questions, you're most welcome.
Thank you, Namrata. It's a really very excellent talk. Particularly, you talked about the role of perovskite deposition and the inverter structure is really more valuable information. Yes. Okay, this is a question and answer time. Okay. Audience may raise some questions.
Where do I see the questions?
Yes, yes. Okay, no problem. I will ask, ma'am. Already erased in the chat box. Someone asked, why that organic hole transport layer is not unstable in the perovskite solar cells?
So as we know that the organic materials are more susceptible to oxygen and moisture, if we have an inorganic layer, it makes it more stable. So it is the property of the organic material itself. the more, compared to inorganic, we all know that inorganic can absorb moisture and oxygen faster, which
Yes.
degrades the perovskite.
Yes. Okay. One more question. Can you tell us the thickness of nickel oxide film? In case the thickness is less than 20 nanometer, how it is possible to get the XR data like that he asked?
Yeah, so it's a nice question. We optimized the thickness, and the best thickness, the best efficiency was obtained with 40 to 50 nanometer of nickel oxide. Yeah, I can understand with 20 nanometer it's not possible, and
Must
even
possible, yes.
yeah.
How lifetime can be calculated from the log intensity versus time plot from the time resolved FL spectroscopy, fluorescence spectroscopy.
Okay, we have an equation for that, right? We fit it, we take the TRPL data and we fit it with a bi-exponential law. So maybe I cannot recall the entire equation, but you should check it. We can calculate the lifetime from there.
Okay, okay. So any more questions, audience? Okay, ma'am. I think no questions.
Okay.
Okay. Once again, thank you for your nice presentation. Okay, thank you so much. Kamlan.
Sir.
Okay. You can allow Dr. Balamurugan. Balamurugan is the next speaker. You could see in the list Balamurugan J.
Yes, sir. Earlier he was there, but now he left, I think. You can call him, sir.
Okay, he is in the list. Now I could see Balamurugan J.
Ask him to reconnect, sir. His video is not connecting.
Okay.
Yes, sir. Balamurugan, sir, you can share your screen. Please unmute your audio.
Balamurugan. Please. Okay.
Yeah.
Okay. Yes.
Start. Share screen. Post to the doctor. Start. Okay, start. First one. Okay. Maybe it's unmute already. No, there. Talking. Yeah.
Yes.
Okay.
Okay, okay, sir.
Please.
Now you can introduce, sir.
Okay. Welcome, Dr. Balamurugan. Balamurugan, is audible?
Yes,
Are you,
yes. Mm.
are you there?
Yes, yes. I can.
Okay, okay.
Mm.
Okay, I want to introduce Dr. Balamurugan. Dr. Balamurugan currently working as a research professor in Chungpung National University, South Korea. He received his PhD from Department of Chemistry, Anna University, Chennai, in the year of 2013. Then he joined as a postdoctoral researcher, Chungpung National University, South Korea, in the year of 2014. Then he received a Korean Research Fellowship, KR of the Chungpung National University from 2015. He gave several invited talks in the international conference and seminars. He received a best oral presentation award in various international conferences and seminars. Also, Dr. Balamurugan performed as a convener and a conference chairperson in several conferences. His main research industry is energy storage and conversion devices, including supercapacitor, lithium-ion batteries, solar cell, fuel cells, and biosensor. He has published more than 50 papers in RSC, ACS, John Wiley, and elsewhere. Actually, he recently published some paper, more than 10 impact were. For example, advanced material, advanced energy materials, small and nanoscale, etc. He got 2 patent and also 2 book chapter. Balamurugan.
Yes.
Okay.
Yes, doctor.
Okay, thank you. Once again, welcome to you.
Okay.
You can start your presentation.
Okay. Thank you, doctor. Thank you. So, good evening to all. So, today I'm going to discuss about the recent advances in emerging 3D nanostructure based materials for energy conversion and energy storage. So, energy conversion, especially water splitting, and energy storage, metal air batteries. Okay. Just next. I don't know. Today,
Yes, you can do.
today I'm going to detail discuss about the material synthesis and applications, both applications, especially metal air batteries and overall water splittings. So I don't know, I have some problems. Rotating. How can I speak? Okay, doctor, I don't know, maybe some problem.
Okay.
It may be rotating.
It's a technical page. 5
Or
minutes
just
later, I'll continue.
just 2 minutes or 3 minutes.
Okay.
Technical problem.
Wi-Fi issue. Wi-Fi. First mute and
Sorry for the late. Due to some technical problem, it takes some times. Maybe they will rectify soon. Kamalan? Kamalan?
Sir.
Could you make unmode to Balamurugan?
Okay.
Only, not video, no, at least the speaker.
Okay, where is my?
Balamurugan,
Hmm.
just my suggestion, instead of your PC, maybe you can use laptop also. It's better.
Oh, laptop only I am using, but there is a problem. MacBook.
Okay.
It's okay. Hmm. No, no, not that one. University one. This file. Oh my. Not this file.
This one. Okay.
Different file. Different file.
Okay. Share. Share.
Unstart. Technical issue. I can use my desktop. So today I'm going to discuss about. It's okay. Can you hear?
Yeah, I could care. Okay, you can continue.
Okay. Today I'm going to discuss about the recent advances in 3D emerging nanomaterials for metal air batteries and overall water splittings. Research content, introduction about the materials and the hydrogen protections. Usually, what is the purpose of the hydrogen and what type of material can apply for energy storage as well as energy conversion devices, and experimental sections including material synthesis and the resultant discussion about the material and electrochemical performances. So the energy, everyone know the energy. So three different type of energy viable techniques is available to produce energy. One is the coal converted into coke. During the coal conversion to coke, lot of carbon monoxide is released and pollute the environment. And other techniques, so we are using some natural resources, including, so, nuclear power plants. When we are using the nuclear power plant, it pollutes the environments. And finally, in order to avoid this kind of pollutions, so especially the environmental pollutions, we need to use the renewable energy resources. So what is the necessity of renewable energy resources? So different type of energy resources available. So due to the human problem as well as the resources, so effect of the carbon monoxide releases and the environmental pollutions, we want to go the renewable energy resources. So you can see the coal converted into coke. It is one of the previously available methods, viable methods. And other methods, a lot of the diesel, oil, everyone used by car that pollute the environment during the vehicles movement. It pollute the environments. So in order to avoid this kind of issues, we need to go towards the renewable energy resources. It may be more safe in future. Why the hydrogen fuel cells? So what is the purpose? Why the hydrogen is very important? So the hydrogen fuels compared to the other available fuels like gasoline, diesel, and natural gases, hydrogen fuels giving more advantages, especially specific energy is higher and internal combustion is very high. That's why the hydrogen energy is giving high efficient, and it is very convenient methods compared to the other diesel or gasoline or natural gases methods, and very quiet. It never create any noise into the environments, and it may be more clean. That's why the people nowadays going to the clean renewable energy sources, and these kind of energy sources towards the electric vehicle cars and transportations and future industries. So this is our purpose. So application of hydrogen fuel cells. So what type of applications is currently available, and what type of applications we are going to achieve in futures? So current usages.
So different type of current vehicles, especially hydrogen fuel drones and fuel cell vehicles and rockets. So many industrial usages currently used in some advanced countries. So especially some technological country in futures. So what type of the materials or what type of the vehicles or what type of the future usages like a home as well as the power plants and hydrogen aircraft, so many fuel we can expect. So why hydrogen productions via water splittings? So different type of methods is used for the hydrogen productions. Why we are choosing the water splitting, especially for hydrogen productions? So different type of methods like a coal converted into coke, we can get so many hydrogens on oil, natural gases. So especially electrolysis, why we are going to for electrolysis? The electrolysis just you can see just 4%. So compared to other techniques, the electrolysis method is very low because we want to grow to the next levels. So previous methods, what methods available in commercially hydrogen productions like coal, oil, natural gases, it have advantages. You can see the advantages very low compared to the disadvantages. The disadvantages you can see the carbon sequestrations and purification of the hydrogens very difficult. It is one of the challenging tasks for the conventional methods. That's why we want to go the hydrogen with the high purity, and the carbon dioxide, it maybe it pollute the environments. That's why the zero carbon dioxide emission is very important, and eco-friendly method is also one of the challenging tasks in the future. Another one thing, the water splitting technology has very simple and scalable methods, and we can get renewable energy conversion devices. And only one disadvantages when we are going to water splitting methods, the fabricating the water splitting with the conventional electrocatalyst like a noble metals, platinum, carbon is act as a cathode, and ruthenium or iridium oxide act as a anodes. Then we want to make some electrocatalyst, especially noble metals. That's why in order to avoid these noble metals, we need to develop the new catalyst, and the catalyst should be low cost and highly durable. Water splitting and issues. What is the current issues? What is the mechanism in water splitting? You can see the anodic part. Anodic, usually oxidation happens, and the cathodic part, usually the hydrogen release, and the anodic usually the oxygen releases. The anodic, usually the commercial anodic water splitting materials is iridium oxide or ruthenium oxides, and commercially hydrogen evolution reactions happen by platinum and carbon based materials. You can see the precious metals and issues. Why we are not going to use the precious metal, especially noble metals? The noble metal have high catalytic activity, but the cost is very high and natural scarcity. The scarcity, very high scarcity. That's why we need to move towards the low cost and non-noble metal based catalyst. That catalyst should be highly stable, and that catalyst should be low cost and simple and scalable technology. You can see when we are going to fabricate these catalysts to electrode materials, we need to some polymer binders. When we are using polymer binder as well as conductive agents, that conductive agent and polymer binders, while during the stability test, especially the durability test, it degrade easily. The polymer easily degrade because the sort of you can see the KOH media or sulfuric acid media, basic media or acidic media, it easily dissolved, and the carbon corrosion will happen easily. Then these binders may be reduce the conduct stability. You can see the HER, but the first cycle, the potential will be very high, or potential is very low, and you can increase the cycles more numbers, then the potential you can see from towards the higher potential, more potentials. And OER also same. You can see the red color one is the one first cycles, and when you increasing or number of cycles will be increases, then the potential will be towards going to the positive directions. Then from this study, from this measurements, we can say the commercial available catalyst is not stable. Then our achievements or our targets should be synthesize a new catalyst. That catalyst should be low cost and highly stable. Water splitting and what is the solutions to solve this kind of problems? Usually the noble metals have high cost, and the catalyst should not have more stable. That's why we need to develop three-dimensional nanostructure. That structure should be high active surface area and more more activity, and the catalyst should be high stability, especially highly durable in acidic as well as basic media. That's why you can see this one. When we are putting one metal, for example, one metal to another metal doping, then automatically the potential shifted towards the lower regions, then we can get high catalytic activity towards the oral water splitting, then the oral water splittings. The merits to the development of catalyst, you can see the catalyst should be highly stability and activity as well as selectivity towards OER. OER means I already told about the OER part is the anodic part and the HER is the cathodic part. So in order to achieve this kind of activity, stability, sensitivity, we need to develop the material is the highly stable and high surface area and more active sites, energy storage devices. So energy storage devices, everyone know the energy storage devices, especially the electric vehicles and automobiles. So nowadays the people going to the renewable energy sources, especially the ion battery as well as metal air batteries. So the commercial available lithium ion batteries, everyone in using nowadays the lithium ion batteries, even though the lithium ion battery have some drawback. That's why people are going towards the air based batteries. Especially what is the problem of lithium ion batteries? When we are using the lithium ion batteries, the lithium ion batteries, we need to use non-aqueous medium electrolytes, and we need to sophisticated instruments to fabrications. That's why we need to the air-based metal air-based batteries we can fabricate easily at room temperatures, especially zinc air battery, and we can also get a high specific energy. Because one of the challenging tasks, specific energy density and the power density for energy storage devices, and the energy storage devices, you can see different type of air batteries available. First, we are telling the ion battery problem, then we are moving to the metal air batteries. Then from the metal air batteries, we have to choose which type of metal air battery is best. Then you can see the lithium air batteries have higher energy density, even though the lithium air batteries, we are using some non-aqueous electrolytes. That's why it is safety issue will become. That's why we need to very friendly manner and simple fabrication technology. That's why we are going to zinc air battery. You can see why we are choosing zinc air battery compared to other metal like aluminum or magnesium. Aluminum and magnesium is not reachable. That's why we need to rechargeable batteries, especially zinc ion batteries. The zinc ion batteries, you can get the maximum performance from the electrodes. You can see the different type of electrodes and the electrolyte used for the metal air batteries. Even though the anode means we are using, for example, lithium ion battery means lithium act as a anode, and zinc air battery, zinc act as anodes, and electrolyte we can use any basic or acidic electrolytes, and the cathode should be, the air cathode should be more stable, because the air cathode need to achieve the bifunctional activities, especially OR and OER properties. Zinc air battery principles, you can see the zinc air battery mechanisms. And zinc air batteries, two type of reaction happen in the metal air cathodes, especially OR and OER. When we are going for OR reactions, it is complicated process, and the sludges reaction, in order to avoid the sludges reactions, we need to develop the catalyst. That catalyst should be highly active, durable for towards the energy storage, especially zinc air batteries. So another one thing, zinc air batteries, when we are using zinc air battery, the zinc metal also, the easily it forms zinc automatically dissolved, and a passive layer formation over the zinc. Zinc also have some problem. That's why we need to develop zinc based anode and the air cathodes for the next generation zinc air battery applications. So zinc air batteries and issues. What is the problem currently, or what is the issues are in the zinc air batteries? You can see the zinc air batteries, I already told the OR or HER based catalyst platinum. The platinum with the carbon. When we are going for platinum based material, it is highly cost. And the platinum based materials, platinum with the supported carbon, that carbon easily degrade, and the carbon corrosion will be happens, or corrosions. When the carbon corrosion happens, you can see the before carbon corrosions, the carbon easily detached from the metal, detached from the carbon, and the durability problem will become. That's why we need to go the requirement for the material. That material should be high overall onset potential and high active density and uniform distribution of the active catalyst and high volumetric activities, and surface area and pore size is one of the important techniques. Challenging task for the metal air batteries. Metal air batteries, when we are going to fabricate the metal air batteries, we need to consider 3 different type of, the available ingredients, especially air cathodes and metal electrodes, especially zinc means zinc air cathode, zinc air battery means zinc based electrode, and electrolytes. So these are the current issues. When we are going for metal air based electrodes, the mass loading of the active catalyst is very low, and that catalyst, because of the catalyst is the noble metal, that's why high cost and durability. OER and OR potential also very high. That's why we need to reduce the OER and OR potentials. And in order to avoid this issue, we need to increase the highly porosity and bifunctional activities and durability. And that catalyst should be low fabrications or low manufacturing cost. Current issue of the metal electrode, you can see the dendrite formations, especially the metals easily dendrite formation with the electrolytes. And due to the dendrite formations, the shape easily changed or dissolved into the long-term durability test. And corrosion effects, because the metal easily corroded in the basic media or acidic media. So in order to avoid, then the anodic also we need to develop. And the electrolytes we can develop different type of electrolytes. For example, liquid-based electrolytes. When we are using liquid-based electrolytes, the stability will be a big issue. That's why we need to avoid these liquid-based electrolytes. We need to make a quasi-solid state, especially gel-based electrolytes, and that gel-based electrodes need then some additives. So then it may be increase the performance of the metal air batteries. So these are the performance degradations. In order to performance degradation, avoid this problem, we need to design the materials. That materials should be highly stable and more active sites. You can see different type of materials we have developed in our laboratory. That materials we are first, after developing the materials, we need to optimize which material is best, because we need to optimize the ratio of the material. Then we need to perform the theoretical calculation. The theoretical calculation confirmations, the structural analysis. After structural analysis, we can see the near to zero, the binding energy, the near to zero, the familiar with very high intense peak, then we can choose that material will be more active for OER or 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 HER property. That's why we need to first optimize the material, and that optimized materials we want to perform the materials 3 electrode systems, OER and OR property. And finally, these 3 electrode systems is good, then we can go for fabrications. That fabrications techniques, materials, after fabricating the device, that device should be compared with the commercially available batteries, lithium-ion batteries or energy storage device like a supercapacitors. Then finally, we want to fabricate towards commercialization, because every product should be commercialization. That is our future targets. So metal air batteries, and what is the solutions to solve the problems? Existing technology and the new technology. What we are going to develop the new technology compared to the, because due to the problem of the existing technology, you can see the platinum or ruthenium oxide based catalyst, when we are mixing, because OR happen by platinum carbon, OER happen by ruthenium mixture, because 1:1 ratio of ruthenium and platinum carbon. Then we need to coat the material and act as the air cathode for the metal air batteries. During the long-term durability test, the carbon, due to the carbon corrosions, the metals will be dissolved into the electrolytes, and the stability will be very big questionable. That's why in order to avoid this issue, we need to develop the 3D nanostructure materials. That the structure material should be highly active and more stable towards the aqueous, as well as especially aqueous, the basic media as well as the acidic media. You can see this is the drawback. I already explained about the drawbacks, because the scarcity, poor durability, these kind of noble metals. That's why we need to develop the low cost, highly active and durable catalyst towards the bifunctional activity, especially OER and OR property. That catalyst should have high surface area, plentiful oxygen vacancies, because the oxygen vacancy is one of the challenging issue nowadays in the scientific society. The oxygen vacancy development is helpful to increase the more oxygen absorption on the electrolyte surface, electrode. Then the porosity. The porosity is one of the challenging. This porosity helpful to the electrolyte and electrode. The penetration will be increased because the active area, especially the reduce the dead mass volume of the electrode, and the synergistic effects. When we are going to develop the metal and support material, the synergistic effects, because the coupling interaction between the support and the metal will be very important. Otherwise, we cannot able to achieve the long cycling life and high energy and power density, because the energy and power density is one of the challenging in all energy storage devices, not only metal air batteries, advances. So based on our idea, we are going to develop 3D nanostructured materials towards flexible and wearable metal air batteries. Metal air batteries towards commercialization. You can see the metal air batteries nowadays coming to all electronic gadgets, especially the computers and cars, electric vehicles, and flexible OLD and flexible cranes. So in order to avoid this issue, current issue of the zinc air battery and water splittings, we need to develop the 3D nanostructure based materials. That's why we are going to discuss about the 3D nanostructure material. That material should be hierarchical architectures. In order to get the hierarchical architectures, we need to optimize the compositions of the initial precursors, especially, for example, so you can use the bimetallic systems. We need to tune the mass ratio of the two metals, and you need to tune the mass ratio of the active support also. That is also one of the great issue for developing the hierarchical 3D nanostructure materials. The hierarchical 3D nanostructure materials in our laboratory, we are using these hierarchical development materials for different energy storage, especially supercapacitor batteries and energy conversion devices, solar cells, fuel cell, as well as water splittings. And we are also using this catalyst for catalysis. And this catalyst especially used for the sensing, biosensing applications to detect the dopamine, as well as to detect the hydrogen peroxide, especially who are affected by cancer. That cancer patient and normal patient we can differentiate from hydrogen peroxide liberations. So why we need to develop the 3D nanostructure based materials? So what is the advantages compared to the other nanostructure materials? The 3D nanostructure materials is unique structure. That material have the fabrication methodology is very simple compared to the other technology, and chemically and electrochemically more stable. That material have good flexibility, and especially the transition metal chalcogenates. You can see the transition metal chalcogenates, we can say metal sulfide, metal selenide based materials, especially metal sulfide people are using previously. Nowadays, people moving to the selenide due to the more active sites, and the selenide have more high porosity compared to the sulfides. So in order to increase the more porosity, we are going for metal selenide based materials, synthesis methods. So especially the transition metal chalcogenates, the synthesis conventional methods, we need to grow the transition metal chalcogenate, especially molybdenum or any other chalcogenates. We can get a single layer, and that layers not bulk, because for example, we need to develop the simple and scalable. Scalable is the questionable here for the CVD methods. That is the problem. Another one thing, when we are going for the CVD methods, the CVD methods need high temperatures. So in order to avoid the high temperature synthesis methods, and we are going to synthesize the CVD, we need to use so many different type of carbon sources, especially acetylene and methane gases. That acetylene and methane gas are also polluted the environments, and this, in order to avoid this kind of issues, we need to fabricate the transition metal chalcogenates with the scalable, especially the scalable. We are going for the simple fabrication technology, and that method should be scalable and low cost. First of all, before going to discuss about the trifunctional, especially trifunctional means the OER, HER, and OR properties. When we are going for trifunctional materials, we can use for both applications, especially what I told in the titles, air battery and water splittings. So first, I am going to discuss about first water splittings, because especially water splitting needs two functional groups. One is OER, another one is HER. Another one bifunctional, I am going to discuss about one materials I am using for the zinc air battery. That function also bifunctionals, but instead of HER, we are going to evaluate the OR and OER. So that is called a metal air batteries. Development of catalysts for water splittings. So recently we have published the papers. These papers, you can see the highly reversible water splittings. lot of reports is nowadays coming for the the scientific community, but so many reports we cannot able to get a highly reversibility, because a highly reversibility is one of the challenging task in the water splitting future technology. So highly water splitting means when we are using our materials for both reversibility, for example, so one material acts as a HER, another the same material is acts as a bifunctional for OER, then reversibility is a questionable. That's why you can see these reports, the world first reports for, or the world first highly reversible water splitting we reported into the this kind of materials. You can see the materials, three-dimensional nickel manganese oxyphosphides, how we make the nickel manganese oxyphosphate nanosheets with the 3D nanostructures. You can see the initial precursors and the initial precursors with the monometal, especially nickel oxyphosphides. You can see the sheet is very high thickness. And when we are synthesizing manganese oxyphosphide, the shape is different. The particles always not controllable shapes, and it is different shape and the bulk particles. When we are using as a catalyst, the materials cannot able to penetrate, and the inside materials would be dead mass value very, very high. So in order to avoid that, we are mixing nickel with the manganese with different ratio. You can see first nickel and manganese 1:2 ratio, and the manganese very high. The manganese, some part is remaining like a ball shaker, and the nickel part should be, you can see the seed-like morphology. So it not fully getting the highly tuned structures. Then we are increasing the nickel ratio 1:1, because one nickel and one manganese, the structure will be tuned, then the ball-like structures fully tuned to the seed-like morphology. But it anyway, it is not 100% tuning. Then finally we tune the morphology with the 2:1 ratio of nickel manganese, and we achieved hierarchical structures with the highly porous morphology. This structure further proved by EDX analysis. The EDX analysis technique is one of the good techniques to prevent the number of elements. So the presence of the elements, sorry. Structure and morphological investigations. When we are making the materials, we need to study the in-depth the structure as well as the morphological investigations. So first of all, we are going for the structural analysis. Our materials, the fully matching with the nickel oxyphosphides, because the nickel oxyphosphides, the JCPD is fully matching. When we are doping the manganese into the nickel, the shift of the higher intensity peak, because 210 peaks will be shifted towards the higher regions, 2 theta value. You can see the manganese, this is the, the structure of the crystalline structure of the nickel manganese oxyphosphides, and this high synergistic effects and the metal compositions is confirmed by XPS analysis, and the structural property, especially surface area and pore size, is proved by BD analysis, nitrogen adsorption desorption analysis. You can see the nickel, manganese, and oxygen, especially the phosphorus, we can get the high binding energy. These binding energy, especially in metal binding energy, higher binding energy compared to the bulk nanoparticles, and the oxygen have metal oxygen p bonding. From the study, our material confirmed by nickel oxygen, because metal oxyphosphides, and the phosphorus containing oxygen, this phosphorus oxide is further confirmed this material containing oxyphosphide, because metal oxyphosphide formations. And this material further evaluated by TEM analysis. The TEM analysis is intrinsic, the morphologic analysis. The TEM, you can see the ultra thin nanostructure and wrinkled nanostructures, and these SAD patterns shows the polycrystalline activities, highly crystalline natures. And from the HRTM analysis, you can see the highly crystalline and the layer distance. We can calculate the layer distance, the despacing value to despacing value. It is fully matching with the XRD. Then for this confirm this material is 100% nickel manganese oxyphosphides. This nickel is 2 and manganese 1. I didn't mention here, but mentioned in the manuscripts. And further, this study is confirmed by STEM analysis. So this highly contrast image shows the material is ultra thin and highly flexible, and this material's elemental presence or existing elements confirmed by STM EDS analysis. From STM EDS analysis, mapping analysis, you can see the nickel, manganese, oxygen, and phosphorus are homogeneously distributed on the ultra-thin nanosheets architectures. First of all, we are confirming the morphological and structural analysis. We are going for the catalyst for towards the water splitting. That's why we need to evaluate first OER performances. From the OER performance, and these OER performances is run in the 1 molar kVH, and this OER performance is run in 3 electrodes configuration systems. From the OER performances, first we are polarization curves for different active materials. Especially you can see the ruthenium is the commercial available materials. We are comparing with the commercial available materials, the potential, the over potential, which one is very close to the, because the really 1.23 is the overall water splittings, but in OER case also we need to close towards the lower water potentials. That over potentials lower means that is highly active towards the OER compared to the other counterparts, especially outperform to the commercial ruthenium oxide based materials. And these details, the LSV zoomed view we are seeing, because especially everyone is calculating the ton, because the lowest the current density, the load current density showing the 189 active materials, the conventional materials have 240. From the study we conclude our material is better than the conventional material, especially ruthenium oxides. And these materials kinetics is confirmed by the Tuffle plots. The Tuffle plots, which one have lower Tuffle value, that should be have higher kinetics potential, higher kinetics, electron transport kinetics. From this Tuffle plots, we conclude our materials almost close to the ruthenium. Then our materials have higher electron transport kinetics. And these materials we are comparing with the recent reporters, the metal chalcogenate based material, transmetal chalcogenate based materials, our material showing lower over potentials. So then our material is one of the best material compared to the other reported materials. And the surface area, I already explained about the BD surface area. This study confirmed by the electrochemical surface area. When we are going to evaluate the surface area, then CDL value, that area should be the non-Faradic area. Then we also confirmed our material have high surface area compared to the other material. This due to the hierarchical 3D nanostructure and 3D ultra thin nanostructures. And we also confirmed the stability. The stability we are running into the chronopotentiometric techniques. The chronopotentiometric techniques, the high current density. Usually the maximum reports reported 10 milliamperes as well as 100, but we are reporting higher current density. Stability is very one of the challenging. And we also achieved the high current density. Our metal is highly stable, and further proved the 5000 cycle, before 5000 and after 5000 cycles, the potentials, you can see the over potentials does not change. It is obviously same potential is observed after long-term stability. And HCR performance, the HCR performance is also performed because it is low resolution figures and these are high resolutions. You can see the ton, we achieved the platinum. This is commercially available materials, platinum. The platinum have 62 millivolts, the over potential, and our materials almost close to the platinums. So these studies tell we can replace the platinum based catalyst. And the electron transport kinetics further confirmed by HCR performances. The electron transport kinetic, the Tuffle value is very lower and it is close to the platinum. Then our catalyst is a highly electron transport kinetics, and our catalyst showing lower onset over potentials. And the surface area of our catalyst is higher than the other comparative catalysts, and the stability is confirmed. You can see that this is the negative window because the OER is the positive window. Then the stability almost stable around 36 hours. Then this study further confirmed our material is highly stable in the aqueous kevocation media and highly active towards the HCR activity. After HCR and OER, we want to go the bifunctional activity, because already we confirmed by the 3 electrode systems and we are fabricating the device. And before that, I want to say, I forgot to say this matter. This material you can see nickel forms, because we are growing the materials over the nickel forms, and we are performed all characterizations. And finally, when we are going for the reversibility, because especially the reversibility test, the nickel form is also act as a catalyst. That's why in order to avoid this issue, we are also growing the material into the carbon cloth substrates. Then the carbon cloth substrates, you can see the almost similar, the over potential observed. Then we also performed first the HCR and OER, the lower current density, the reversibility. You can see the reversibility is maintained in the 3 electrode system. This is in the 3 electrode systems. And we are also comparing our catalyst to the commercially available catalyst. And the overall water spreading based on these bifunctional activities, our catalysts have showed the potential of 1.51 volt. But the commercial catalysts, especially ruthenium oxide and platinum, the couples, that is because the ruthenium oxide is the OER and the platinum carbon is the HER catalyst. Then we want to mix or because they make a device, and finally we got the performance. From the study, we conclude our material outperform than the commercial available catalyst. Even this high current density, when we are going for high current density, the active catalyst, because the commercial catalyst, you can see the potential is very high, but our catalyst achieved around 500 milliamperes, 1.72. So from the studies, we can confirm our material is highly active in even high current density, and our catalyst is the highly active catalyst towards the OER and HER, and yes, finally achieved the potential of 1.51, and water spreading, overall water spreading also better than the reported catalyst. And we also want to, when we are going to prove our materials towards the commercializations, then we need to prove the theoretical value of the hydrogen and oxygen evolutions. From the studies, you can see the hydrogen and oxygen evolution almost equal to the theoretical value. And we also tested with the different current in the chronopotentiometric test, and our catalyst almost 60 hours is more stable for all different current density. And the reversibility, you can see the reversibility for overall devices. The device almost maintained. There is no distortion happen. So this study confirm, because almost 24 hours, the study confirm our material is a highly reversibility. So it is not enough to prove our catalyst is a highly stable or less activity. After these electrochemical performances, we need to confirm by the morphological and the structural investigations. So in order to prove the catalyst is more stable, then we need to take the oxygen reduction OER part and HER, because hydrogen evolution HER electrode. But here oxygen parts, we are oxygen generation, then maximum electrode is maximum oxidized easily, and hydrogen part may be reduced. So in order to prove the more stable towards the bifunctional activities, we need to take hydrogen HER side electrode and the OER electrodes. That's why we are also evaluate the HER side electrode and OER side electrode, because both are same electrode. Even this is a device, and even though we need to confirm the both electrode materials is more stable or confirmed by the SCM EDS analysis, you can see the phosphorus, because the phosphorus is easily degraded into or converted into oxides. From our case, the phosphorus is fully retained in case of the HER side electrode and the OER electrodes. And you can see the initial one. This is initial one for nickel, manganese, and oxygen phosphorus. And after HER and after OER parts, almost the potential of the nickel 2p 1/2 peaks little shifted towards the higher region in case of manganese and nickel. And in case of non-metallic systems like phosphorus and oxygen, it shifts towards the lower regions. Development of catalyst for air battery, zinc air batteries. So we are developing. I already explained about the zinc, usually used for the negative electrodes. And when we are going to develop the zinc-based materials, there is corrosion effects, and the passivation also happen. In order to avoid, we also growing the zinc-based catalyst in the and used as negative electrodes. And the 3D nanostructures is a air cathode. That air cathode is act as a air cathode also air cathode material, and we all finally fabricate the newly developed zinc nanorods, 3D nanostructures, and the air cathodes, and fabricate the quasi-solid state electrolytes, especially PVA, Kevokash media, and we fabricate the device, especially the flexible energy storage zinc air batteries. Before going to fabricates, we need to evaluate one by one, and morphological analysis. The morphological analysis, first we want to prove we are growing directly the carbon cloth. The carbon cloth, you can see the uniformly the ultra thin nanosheets are grown over the carbon cloth. The zoomed view, because the high resolution view, you can see the every carbon cloth, every nanosheets, each nanosheets interconnected with each other, and there is huge porosity. This porosity may be helpful to the ion transportations and increase the electrostatic activities, and the thickness of the sheet is very thin, then the active site is more high, especially the electroactive site is more high. And These elemental distributions confirmed by STM EDS analysis, nickel, molybdenum, oxygen, selenium are uniformly or homogeneously distributed over the area. From the studies, we conclude our materials contains nickel, molybdenum, oxygen, and selenium. So after fabricating the materials, we need to not only prove by the theoretical experimental, we need to prove by the theoretical studies. From the theoretical studies, we are mixing different ratio, and finally we got the 1:1 ratio, nickel and molybdenum. So you can see this in this intensity is very close to the energy is very high compared to other materials. So this material, you can see the intensity of these materials. Then from the studies, we can say our material is highly active, and this material can apply for the metal air cathode for metal air batteries. So the catalyst should be further studied by intrinsic morphology by TEM. From the TEM analysis, you can see the ultra thin nanosheets and wrinkled nanotubes, and the high resolution TEMs confirm the highly crystallinity, and the FFT patterns also confirm these hexagonal shapes of the nanosheets. Because this is the face will be matched with the hexagonal shapes, and this is highly polycrystalline natures confirmed by STM SAED patterns, and STM EDS analysis further confirm the ultra thins and brighters. You can see the metallic brighter area, and the nickel, molybdenum, oxygen, and selenites are homogeneously distributed over the ultra thin nanosheets. Further confirmed by these techniques because the elemental compositions and the binding energy. The binding energy, you can see our materials fully matching with the extra depositions, fully matching with the nickel oxygenates. But our studies, we want to tune the morphology. That's why we are doping molybdenum with the different ratios, 0.25, 0.5, 0.75. When we are changing the ratio, the XPS also shifted. So compared to the other ratio, our optimized ratio having higher current, higher binding energy compared to the other ratio. From the studies, we tell our material, our optimized material have high binding energy with the nickel and molybdenum. And molybdenum, in case of molybdenum, you can see here also the materials, the molybdenum also compared to the pure molybdenum selenites, our compositions have higher binding energy compared to the pure when we are doping nickel with a different ratio. And in case of the oxygen, the oxygens should be compared to the monometallic, because nickel oxygen as well as molybdenum oxygen selenites, the bimetallic selenites is lower binding energy compared to the monometals. And case of the selenium, you can see selenium contains two type of 3x2 as well as 5x2 spin orbitals. This is the metallic selenide space, and this is the oxygens and selenide formations, because selenium oxide formations. From these studies, we conclude our materials contains oxygen, selenium, and molybdenum with nickels and the different ratios. So these materials we are performed in the zinc air batteries. So I didn't discuss about the 3 electrode systems due to the times. The electrodes, when we are going to fabricate the electrodes, because the nickel molybdenum oxide is air cathodes, and zinc rod directly grown over the carbon class is act as a anode material, because in order to avoid the corrosion effects of the zinc, then we are using directly grown materials. And another one thing, the advantage of the zinc directly grown carbon, we avoid the binders, especially polymer binders, because direct growth methods avoid the binders, and we reduce the dead mass. And in another one thing, when we are growing carbon cloth, we can use as a flexible and wearable energy storage devices. And we also performed these materials with the commercially available platinum, carbon, and ruthenium oxides couples. And our catalyst showing OCV higher value compared to the commercial one. And you can see the value in this display 1.43, almost 1.43. And the power density, this is IV curves, because last talk I have seen the solar cells, because IV, they are doing also IV, the potential and the current varying studies. When we are changing the current and the potential changing, we can get the discharge curve, as well as from the discharge curve we can get the power density. This power density of our catalyst, because the nickel, molybdenum, and zinc or nanorods based devices achieved higher power density compared to the commercial available materials. And we also performed the rate performance of the devices. When we are going the open circuit potentials 1.4, almost the potential, the cell voltage maintains. And when you increase the current, the cell voltage reduced, again increasing 5, again 10, then again increasing the 5, it almost retained. From the studies, we confirmed our device have high rate capability. And our materials compared with the recently reported materials. And we also performed the practical applicability and glowing LED, and the toy fan run effectively, and the LED also glowing almost 24 hours. The charge discharge, because the long-term discharging curve, from this curve we calculate the specific capacity, and from the specific capacity we calculate the energy density. Finally, the great challenging issue of the stability. Stability is one of the challenging issue. I already explained about the stability issue. So we also performed our catalyst with our flexible energy storage devices. That energy storage devices, almost you can see the potential, because these two, almost two, yes, this potential is maintained. This part fully is OER part. Sorry. This part is fully OER part. This part fully OR part. Suppose your catalyst is not active in OER, it go higher because it is not maintained. But suppose your material is not active, more stable in the OR part, it may be coming down because the potential will be vary. You can see our material is almost stable for 200 hours. You can see the first and final stage almost the round trip efficiency, because from this lower, because this is cathodic part, this is anodic parts, the round trip efficiency almost retains. And in case of the platinum and ruthenium based catalyst, the potential is increased because due to the corrosive effects and the carbon corrosions and the dissolution of the active materials. And finally, you can see the different charge discharge curves with different comparative materials. Our catalyst, you can see the anodic and cathodic, the potential difference will be very close compared to the commercial available catalyst. From the studies, we can see our catalyst is more active towards the metal batteries. So we also tested with the commercial catalyst device, the electron transport kinetic, because indirectly we can say from this impedance, electrochemical impedance study, electron transport kinetics for our devices, even our device with the foldable conditions, even different foldable condition also, you can see the almost retain the high frequency semicircle and low frequency semicircle, because the electron, this is the low frequency semicircles. From the studies also we can say our device have high electron transport kinetics. In order to implement our device towards the commercial application of the flexible and wearable, we want to test with the different test bending and twisting, because you can see different bending angles and twisting angles. While we are running the charge discharges, we also bending and twisting with the different angles, and the anodic as well as cathodic path almost retained. The round trip efficiency almost retained. From the studies, we conclude our material is one of the best materials and best device for the commercial energy storage, especially flexible and wearable energy storage devices. Morphological. In order to prove the outstanding stability of the materials, we need to test the morphological. You can see the morphology, and STM EDS color mapping further confirm the seleniums almost retained after long-term stability durability test. And the XPS also, I already explained, the metal-based material shifted towards after stability, shifted towards a little higher, not obvious. Then the non-metallic base, little lower regions, it will be moved. And finally, I already explained the bifunctional activity. That's why I give one example and for water spreading, another example for air battery. And now I am going to discuss about the trifunctional activity, because my topic is the trifunctional activities. One material should have trifunctional activity. That is one of the challenging tasks in the research community. So we also recently reported these materials even maybe we take very short periods, and maybe within 3 months we have reported in the journals of JUSMALS. We have developed the materials cobalt manganese selenites, and the material should be oxygen dominated, because the oxygen dominated is one of the challenging issue. Oxygen, when you increasing the oxygen vacancy, or when you develop the oxygen vacancy or oxygen dominated into the material, that material should be long-term durability and high absorption ability towards the OER and the OR property. And we also performed with a different morphological and structural analysis. And finally, these HER, OER performances and ORR performances. From these studies, the material should be trifunctional, and finally we fabricate the device and we tested with the different electronic performances. From these electronic performances, we conclude our catalyst is one of the best catalysts. for the metal air batteries. So I want to discuss a detailed about this work because these materials are used as a trifunctional active materials. So this synthesis techniques is little simple techniques compared to the conventional technique, because the strategy 1 and the strategy 2, because you can see the strategy 1 is our new technology and the strategy 2 is the already available conventional methods. When we are going for strategy 1, that method is the very simple methods. We are mixing with the initial precursor of graphene oxide and metal precursors, and finally we get some intermediates, and finally we pyrolysis into the nitrogen atmospheres or organ atmospheres. No any hazardous sources we are using for the development of the catalyst. In case of the conventional catalyst, in order to get the metal nitride based materials, we need to use ammonia. Ammonia is one of the hazardous gases, and we need to use ammonia gases. We need sophisticated instruments and sophisticated rooms. So in order to avoid these ammonia based gases, we are developing the new strategy. This is our proposed strategy. And another one thing, when we are going for the ammonia methods, first we need to develop metal oxide, and then metal oxide should be converted into metal nitrates using ammonia methods. When we are going to convert into metal oxide to metal nitrate, metal oxide not fully converted into metal nitrates because the metal particles should be high, big size. The outside surface area may be easily converted into metal nitrate, but inside it's not converted into metal nitrates. Another one thing, when we are going for two-step methods, that methods we cannot be able to get the coastal materials. One problem is the particles is not controllable because particles with different sizes and no crystal formations. From this problem, we need to develop core shell, because the core shell, what is the advantage of core shell compared to the non-core shells? When we are going for core shells, while going for long-term stability, the shell should be prevent the active catalyst from the degradations. So that's why we need to develop the core shell with the simple and scalable method. This is our challenging task. So development of catalyst towards the trifunctional activities. This catalyst first confirmed by FECM. You can see the FECM highly porosity, and the graphenes and metal hybrids. You can see the high area look like a high porosity and a high surface area. And from the TM analysis, the ultra thin particles, because the particle size is very, very small. The ultra thin particles are homogeneously distributed over the Ng nanosheets, nitrogen doped graphene nanosheets. And nitrogen, what is the role of nitrogen? Nitrogen should be increased compared to the normal graphenes. Nitrogen is the highly conductivity, and the electron transport kinetics will be high compared to the normal graphene. That's why we are using nitrogen doped graphene. And these catalysts, you can see the particles almost around 2.5 to 3 nanometers, and the particles is encapsulated by some shells, small carbon, Ng, nitrogen doped carbon shells. So these may be enhance the conductivity and enhance the electrochemical stability towards the trifunctional activities of OER, HER, and ORR. And the Kylie crystallinity confirmed by STM EDS analysis, and STM EDS analysis. You can see the particles are homogeneously distributed over the nanohybrids, core shell, especially core shell nanohybrids. So this study further confirms our materials contains the existence of the elements like copper, molybdenum, oxygen, nitrogen, and carbon. So the material should be confirmed by the XPS analysis. The copper, you can see copper 3/2 and 2 type of binding energies getting. So in case of the copper 1+ compared to the copper 2+, it is more active. That's why we also achieved a high copper 1+ compared to 2+. And we also get molybdenum nitrate bonding from the molybdenum high resolution spectroscopy. And the molybdenum also different type of states, 3+ and 4+. And the oxygens, we can get oxygen carbon because carbon carboxyles, and nitrogen oxygen bonding also. And the presence of metal oxygen nitrogen confirms our material contains metal oxygen nitrogen, confirmed by this XPS analysis of the oxygen 1s. And nitrogens, we can get 3 different type of nitrogens: pyridinic, pyrrolic, and graphitic nitrogens. Compared to the graphitic nitrogens or periodic nitrogens, pyridinic nitrogen is more active towards the electrocatalytic applications. So we also achieved the high intensity of the pyridinic nitrogens. And molybdenum nitrate further confirms our material contains metallic nitrate bondings and carbon. You can see before the initial graphene oxide contains carbon oxides, carbon C112O is very high intensity. After reduction into the high pyrolysis techniques, then the bond will be reduced and the carbon-carbon bond almost we can get the perfect carbon-carbon bonds. And from this the structural analysis, the BET surface area further confirms our catalyst. But in case of the nitrogen doped graphene has higher surface area, and when we doping with the monometallic copper and molybdenum and the bimetallic system of copper molybdenum sulfides nitride have high surface area, it's almost near to the nitrogen doped graphene. Because why the nitrogen doped graphene is higher? When the metal doping, the surface area will be reduced. But in case of the conventional methods, conventional method catalyst, we calculate B, because the represent the B is the conventional method catalyst. And that catalyst, I already told that is represented as a crucial, but here just a bore because just observed on the surface of the NG. And the conventional methods have lower surface area compared to the other monometallic systems.
Dr. Balamurugan, sir, already 10 minutes over. Possible finish shortly.
Okay. Just going to finish. So the catalyst first confirmed by ORR performance, because ORR is one of the kinetic issues problem, and this ORR performance is sludge kinetics reactions. So we want to compare the ORR performances, the commercial catalysis platinum carbon. So our materials containing halfway potential, because the E of is one of this value is very important, because the E of value compared to the platinum carbon based materials, it is lower. And this onset potential also is lower than the platinum carbon. And the Tafel plots confirm the value of the materials, the copper molybdenums is lower compared to the monometallic systems counterparts, and the platinum carbon materials almost similar. And we also run the catalyst, the LSV, with a different speed, because this is in the oxygen atmosphere and different speeds. When increasing the speed rates, and the current will be increases towards the negative regions. And from this current, we also calculate the KL plots. From the KL plots, we confirm our material should be 4-electron transport kinetics, because 4-electron achievement is very important for ORR. And these all performance is evaluated by or measured by the RDE, because rotating disc electrodes, because the RDE disc electrode is not confirmation studies. We want to go RRDE, because RRDE is one of the techniques to find or calculate the hydrogen peroxide liberations, because hydrogen peroxide liberation is lower, that catalyst should be high, good, compared to the hydrogen peroxide liberation very high materials, because the hydrogen peroxides may be make a corrosive property of the electrode and maybe reduce the durability. And you can see this one is disc, this one is ring current, because this ring current and disc current almost, from this ring current, disc current, we also calculate the hydrogen peroxides, because you can see this hydrogen peroxide yield. Our catalyst almost, because here our catalyst almost less than 15s or almost 12 or 10. Then our catalyst is lower hydrogen percentage yield. Maybe so many catalysts containing more hydrogen percentage yield, maybe it destroy the stability. And the number of electrons is almost equal to the platinum commercial catalyst. And you can also run the RRD test with the different speeds. And the methanol ability, because the methanol tolerance ability is also another challenging, because when we are using for fuel cell applications for the catalyst, methanol tolerance ability is very important. When we are using our metal catalyst, the potential almost retained, because there is no drops. In case of the platinum, it drops. It may be almost less than 50 relative current percentage is reduced. So from the studies, our catalyst is highly methanol tolerance ability. And OER as well as HER property, as per previous discussion, you can see our catalyst for OER, iridium. Previously used for ruthenium, but in case of the iridium, is more active compared to the iridium in the aqueous KOH media. That's why we choose the iridium for this work. And the iridium based catalyst is lower compared, is higher potential compared to our material. That's why our catalyst is better than the iridium based even other catalyst. And the the kinetics is very higher, or it is close to the iridium oxides, and the stability confirmed by the corona potentiometric test. And our catalyst, the OR potential is lower compared to the recently reported material in the OER part. And in case of the HER, you can see the platinum carbon, the OR potential and our catalyst almost near to the platinum carbon, and other catalysts may be higher than our catalyst. and the kinetics by Tefl plants also confirmed our catalyst is the better electron transport kinetics, and the stability confirmed in the case of the HER. It is also highly stable at a high current density, and our catalyst is a lower over potential compared to the other catalyst. So based on the performance, because first I performed ORR and OER and HER performances. Based on the three trifunctional performances, we want to fabricate two different devices. One is zinc air battery, another one is water splitting devices. First, I fabricated our electrode as act as a air cathodes, and zinc act as a anode. And finally, our fabricated electrodes getting the higher power density compared to the conventional, and that power density is higher than the recently reported materials. And our catalyst is containing higher or open OCV value compared to the conventional, the couples, and the specific capacity compared to the platinum ruthenium, the material getting higher specific capacity. From the specific capacity, we also calculate the energy density also higher, and the stability. You can see previous catalyst we are using the ruthenium, and in case of the iridium we are using, and this may be almost more than 112 hours, I think. The in case of our catalyst is stable up to 400 hours. You can see the anodic sites and the cathodic sites almost stable, because the round trip efficiency between the anodic and cathodic is maximum stable compared to the conventional cathodic. Conventional cathodic catalyst, you can see the potential is towards the almost 2.5 in the OER part. It is not stable, and it also dropped less than 0.6, because air cathode should be maintain this kind of the potential reversibility, because the potential almost near to the 1.2, the potential is good compared to the other catalyst. From the studies, our catalyst is highly durable, and the gap between the gap and this is charging and discharging, the charging potential the gap is very low compared to the conventional. And the flexibility test also confirmed with a different bending test, and we are also glowing the light with a different bending angles, and the rate capability performance also confirmed by the long-term durability, long-term stability in the discharging current. And these morphological investigations further confirmed our material after zinc air battery performances. Almost the peaks almost retained, even the nitrogen also almost retains, and the morphology you can see the co-shell is prevented the active catalyst from the degradations. From these studies, the co-shell is the one of the active media to prevent from the degradations, and the materials are uniformly distributed because the element distribution is uniform. From these studies, we conclude our material is more stable towards the zinc air battery and overall water splitting. So because from this HER and OER property, previously ORR and OER property, we fabricate the zinc air battery, but now HER and OER performances, we fabricate the water splitting devices. From the water splitting devices, because these both are same catalyst, used as a bifunctional, and we achieved 1.5 voltage and compared to the conventional catalyst. And our catalyst is the better cell voltage performances compared to the reported materials. And we also performed our hydrogen evolution and oxygen evolutions with theoretical value almost similar. And the rate reversibility, I already explained the 24 hours reversibility. From the studies, I also put conventional catalyst. You can see the potential is reduced. Here reduced, in case of our catalyst almost maintained. This HER side, here OER sides, because from the studies our catalyst will be highly reversible. And we also performed with a different current density current, then this potential more stable in the chrono potentiometric performances. And finally, our devices, zinc air battery performed to work out for the overall water splitting. So when we are connecting our zinc air battery in the series connections, the water splitting performed very well. And I also performed with the different structural analysis. The structural analysis confirmed our material is more stable, and you can see our device, the zinc air battery devices. When you are connecting with the zinc air battery devices, it liberates hydrogen as well as oxygen from the overall water splitting devices. Summary and conclusions. With our goal, what is our goal? So because one of the great challenging goals, low cost productions, low cost or low high efficiency or high energy density and power density energy storage and conversion devices. and that device should be long cycle life. So in order to achieve this kind of long cycle life and high performance energy storage and energy conversion devices, especially air battery and water spreadings, we need to develop the materials. The materials should be simple and scalable and cost-effective strategy. That material contains more active sites, and that material should be higher porosity. So these are our challenging tasks to achieve the high energy density, power density, and a long cycling life of energy storage and energy conversion devices. So our 3D nanostructure materials is active for trifunctional, especially OR, OER, and HER performances. The composition of the catalyst, initial catalyst, is very important. When we are making the catalyst, we need to change the compositions. Then only we can achieve the 3D nanostructured materials. That material should be highly active in any applications, especially energy storage or conversion. And that catalyst we need to perform with the air battery and water spreadings. Then we need to develop, before water spreading and air battery, we want to perform OR, OER, and HER. From ORR, we need to achieve half-wave potential, because this is one of the challenging in ORR. Half-wave potential is lower, then the catalyst should be very good, and the OR potential for OER and HER and TEFL will be also very low. That catalyst is better than the other commercially available catalyst. And our catalyst showed the round trip efficiency for 400 hours in the zinc air battery, and the water spreading also we achieved 1.5 voltage, and the available, because we need to go towards 1.23 volt, but everyone trying to that, and the outperformance, our catalyst is outperformed than the commercial couples like platinum, carbon, and iridium. And this strategy, from the studies, I conclude the Kaushal is one of the challenging, because when we are making the Kaushal materials, we can protect the active material from degradations and enhance the stability, and that material should be used for the OR and the OER and HER. Finally, we can fabricate the air battery and water splitting devices. From the studies, we conclude this kind of strategy maybe we can use for the future energy storage and energy conversion technologies. So I want to say our university, because it is one of the top 10 university in South Korea. So we have different type of students in our university. Just 1 minute. Okay. Okay, so due to the time trails, I'm going to next slides, because this is our university main entrance. And so Professor Lee, because he is the vice president of our university, he is our boss. And we have the big groups in our research groups, because more number of postdocs, because around 10 postdocs working our groups from different country and all over the world. And the Professor Lee is one of the leading scientists in the Chonbuk National University, because he continuously got the best research award for last 10 years. And we also working together, because the unity and the discussion with the students is very important thing. We also working together with the different country peoples, and we have the good environments to get a high impact journals and towards the materials towards the commercial applications. So thank you for your kind attention. So if you have any questions, please kindly let me know. Thank you.
Thank you very much, Dr. Balamurugan. Your talk is really very informative and excellent about your recent invention. This is a question answer time. Audience may ask your question in the chat box. Few questions already raised. Dr. Balamurugan,
Okay, please.
can I ask a few questions?
Okay,
Already,
please.
they already raised in the chat box.
Okay, please.
For a sulfide-based material, upon cycling up to 2000 cycles, I found that there is an increasing in capacity. What would be the reason for that?
Sulfide-based materials.
Sulfide-based material, upon cycling up to 2000 cycles, I
Okay.
found that there is an increasing specific capacity.
Specific capacity for which I don't
When
know.
increasing the when increasing the cyclic, the specific capacity also increased. He asked me what's the reason for that increasing of the capacity.
So I didn't discuss about the capacity. I don't understand.
He is telling usually when increase the cycle, maybe it is stable or maybe reduce the specific capacity. But he told his capacity is increased when increasing the cycling. You don't know the reason. He asked just, do you know the reason? And
No, because no. Can he repeat the question? Because here we are not discuss about the specific capacity. Because here we are not discuss about the ion battery.
yes, actually, he is not about your talk. I think he got some.
Yes, because ion battery I am not discussing. Maybe I think this slide. Maybe he thinking the capacitance increasing. Yes, this potential. Maybe he thinking about the potential. I think so.
Okay.
Because this one is air battery. We are not discuss about the ion battery based material.
Okay.
And I also discussed about already specific capacity from this car.
Okay.
I think maybe he is different area. I think maybe he confused and asking questions.
Yes. I request the participant if you have any further doubt
more
about
question
your work,
also,
you
okay.
can contact Balamurugan through his email.
Sure, thank you.
Okay. Any more question? I think no question because of your already you explained everything. I think so. That's why no question. Okay, thank you once again. Thank you so much, Dr. Balamurugan.
Thank
Really,
you.
it's a
Thank you
very,
so
very
much.
wonderful talk. Everybody get more.
Hello.
Okay.
Hello.
Please.
Hello, sir. Balamurugan, sir. Hello.
Okay. Yes.
Sir, my name is Channakeshwar. Just I would like to ask a few questions, sir.
Okay, please.
Sir, normally zinc is having a problem of drying. Just even in dry cell, they are using. How will you overcome that problem normally in your zinc air battery?
Zinc usually drying, yes.
Yes, in presence of oxygen, normally zinc will have a tendency to dry.
Because the zinc side we are not using the air. Only the air we are using for cathode side.
Yes, but still.
But we need to develop the electrolyte should be very important.
Yes, that's
electrolyte. The electrolyte gel electrolyte fabrication is one of the challenging. When we are fabricating the gel electrolyte, making electrolyte, the composition should be perfect. Then the zinc never dried.
Okay.
The composition of electrolytes. The electrolyte role is very important because maximum people when we are fabricated the electrolyte gel electrolytes.
Okay.
It may be dry. It may be rotund or it may be not flexible. Then this problem will happen.
No, for water splitting, you are using manganese based thing.
Yes.
Suppose, are you just mimicking the photosynthesis for water splitting thing? Your catalyst, you are designing based on photosynthetic.
No, my material synthesis towards from the hydrothermal method.
No, hydrothermal method only. Just what I'm asking, based on the photosynthesis, you have taken manganese or you have chosen simply manganese? Sir?
No, just simply mixing of manganese and nickel.
Okay.
Because just a source, basic source only.
Okay. And I thought of based on photosynthesis, you made.
No. It is not related to the
like a kind of a chemical synthesis only by hydrothermal.
Synthesis.
Okay, sir. And one more thing, this surface area, I am suppose after impregnating your nickel or copper, just I have seen your isotherms, the quantity of nitrogen absorbed is drastically reduced after impregnation of your material. That is
No.
manganese or copper or whatever.
No, I compared. No, I'm not comparing with the after or before because I'm comparing
Okay,
with the
okay.
different composition.
Oh, okay, okay.
No, I comparing with the different composition because I also previously explained with the different morphology.
Oh, okay.
Different morphology. Based on the different morphology, I also calculate. Oh, I cannot able to move. That slide I cannot able to go back.
Oh, okay.
That slide because we are tuning the morphology with the basic initial precursors. When we are put only manganese, we get the ball-like structure with the different shapes. When we are making nickel, we get very thick sheet, not thin sheet. Then we also changing the ratio of the nickel manganese ratio.
Okay.
Nickel and manganese ratio we changed it. Then, for example, manganese ratio very high. Some part of manganese not fully converted into sheet-like morphology. Some part like a ball-like structure. Some part only the sheet-like morphology. Then we are also increasing and the tuning the morphology. Then finally we got 1:2 because nickel 2 and manganese 1 ratio is a better ratio. From that 3 ratio only I comparing the morphology. I didn't compare with whatever you told like impregnation. This is just a direct growth.
Oh, that's what I thought is you can see the porosity also, even pore size distribution before impregnation, after impregnation. Actually,
no. This is I compare with the all phosphate, not the even not the precursors also.
Okay.
But I cannot able to go to the slide. I just type.
Okay, Doctor, no problem.
Okay, sir,
Doctor,
that is not the problem.
Okay.
Sir.
Thank you so much.
Dr. Brahm, I have a small question.
Okay, please.
Actually, in industrial aspect, whatever we did, so we focused on only the industrial, maybe
Industrial
commercialization. In this aspect, how much large area the electrode prepared? In your,
How much large area?
Yes, the electrode.
Still now we are preparing maybe 3 centimeters or 4 centimeter like that, but we are not go beyond.
Okay.
We are just like the pilot scales.
Okay, sir.
Just we want to go pilot scale. We are just lab scales.
Oh yes. Okay.
We also planning to make the large scale synthesis, large scale fabrication.
Okay.
But we are not sure because I am honestly say we are not sure that
Yeah,
performance will be great.
Yes, no problem.
Because we cannot able to say the video maybe 100% get performance like higher like smaller size. This honestly say somebody may be hide, but I'm honestly say maybe impossible.
You found a new material, so now it's important to initial screening. Then only we can.
Yes, that's correct because
Yes.
we also tried to develop the industries level.
Okay.
But just the lab scales we are developing.
Okay. I think there is no more question.
Hello, sir.
Okay, please.
Hello.
Please.
Sir, actually, I have some questions, sir.
Okay, please.
So my question is why the over potential should not be high for the air electrode application, sir? If it is, could you tell me what is the range is preferred to be a good air electrode performance?
No, over potentials. What your question is, I cannot able to know because over potential is lower is best. Yes. And over potential should be lower. That is very important.
Sir?
Yes.
Why, sir?
Because
why? If it is high, what happens?
No, over potential higher is maybe the activity is low. Usually, we cannot able to get a high activity.
Okay.
Because our target, because the commercial water splittings, not commercial, that is one of the, we want to achieve 1.23. That voltage we need to achieve, but everyone getting more than 1.5. We are always traveling towards lower.
Okay.
That's why in case of the HER and OER, that both is called overall water splitting because OER and HER. In case we can reduce both, then the device should be lower.
Okay.
Based on this total only, we can get a final water splitting.
Okay, sir. Okay.
That's why I showed previously the first introduction sections because the people are pushing, like that. That is our target towards the lower potential because lower potential lower, we need to develop the best materials.
It may be affect the stability.
Yes, sir. I just that point is clear, sir. Yeah, I clearly understand that you're trying to produce a material should be the over potential should be lower.
Lower, yes. This is our target.
Yeah. I just want to know why the over potential should be lower for a best performance. Why it is directly related to the activity?
No, that's why I told us because the water splitting happen at 1.23.
Okay.
That is normal. Then you can imagine now our potential 1.5, yes.
Okay.
In case our potential high 1.6 or 1.7, the Sludges kinetics will be happen, yes.
Okay.
And that's why we need to going towards the natural water spreading the area media 1.23.
Okay.
That's why we need to reduce because because three reactions happen with the Sludges kinetics. The Sludges kinetics should be low water potentials.
Okay. Right.
In case your material is not performed good, it may be higher water potentials.
Okay, sir. Okay,
due
thank
to
you.
so many
And
reasons.
okay, sir.
Okay.
Then this may be what is the key criterion for the material to be reversible? Like you were selecting for metal air application and the water
No,
splitting.
metal air battery, I'm telling the stability, but in case of the water splitting, reversibility. Because when we are using the only HER performance, we can get a reversibility. Or because every time the power break happen in the device, yes. So in order to avoid this power break problem, we need reversibility.
Yes, sir. What is the key criterion? If I want to produce this particular material, which property I need to optimize to act the material to be a reversible?
Activity is very important.
What activity it is? Sir?
Activity means three different functional activities because one is OER, HER, and ORR activities.
Okay.
And that material should be high activity and high porosity.
Okay.
Porosity means when the porosity you can develop, the electrolytes can easily penetrate into the electrode. Then active surface area also increases.
Okay.
And dead mass.
Yes, sir.
Okay,
Dead
the
mass
time
may
is already
be
30.
reduced.
Yeah. Thank you, sir. I just want to
Give
know.
my contact to Dr. Balam.
Sure, sir.
Okay,
Sure,
please contact
sure,
anytime.
Sure.
Okay.
Thank you, sir. Thank you.
Okay,
Thank you very much.
Thank you.
Thank you, Dr. Balamurugan. So once again, I want to remember that about our next day of this webinar. The second day of this seminar will be started at 10 a.m. by tomorrow. Okay, once again, thank you to participant and our respected speaker.
Oh, thank you so much.
Thank you. It's
Doctor.
very happy, Doctor.
Thank you, Doctor. Thank you.
You did a lot of work.
Sorry for everyone because I didn't expect that the problem will happen.
Yeah, that's no problem. That's no problem.